Hello, this is Miraj Patel, and today we're going to be talking about gas laws, and we're going to introduce our first formula, which is going to be combined gas law formula, and before we talk about that, we're going to be talking about some trends and some scientists that formulated the gas laws. And so before we begin, we're going to go over the variables and the quantity and unit we're going to measure it in. So we have variables, so P is for pressure, which makes sense because there's both P, and pressure is measured in ATMs usually, and then volume is measured in liters. T is for temperature, which is measured in Kelvin. So this is very important. So temperature is always measured in Kelvin, and these can change, but temperature is always needs to be in Kelvin. And then N stands for number of moles, so that's like the only tricky variable out of these four. And number of moles is just measured in moles. And so moving on, so here is our first scientist we're going to talk about, and Avogadro. I'm sure most of you remember from the unit way back when. Avogadro was a guy who made up what a mole was, and a mole is 6.02 times 10 to the 23rd particles, just FYI. And Avogadro's hypothesis stated that at the same blank and blank, which is temperature and pressure, so at the same temperature and pressure, equal volumes of gas must contain equal moles, or N. And it sort of makes sense because remember, number of moles is sort of just the number of particles inside, and volume is just how large this container takes up. And so if you have same temperature and pressure, that means there's the same speed of these particles, and pressure means that there's the same force pushing down on these containers. So if you have the same speed and equal volumes, and they all have the same pressure, so same amount of force is pushing down, there's equal number of molecules or moles in this. So, and this all has to do because there's the same number of collisions and same number of force pushing down, so they're always the same volume. And he figured out that at 1 atm and 25 degrees Celsius, and we have a volume of 1 liter, we have a certain amount of number of moles, so which is pretty cool. And Avogadro's law, so this is the real thing, the most important thing you should take away from the slide, is that if we increase the number of moles, then the volume will increase by the same factor you increase the number of moles. So here we have a balloon, so we have 1 mole of helium and then 2 moles of helium, so we added 1 mole. And so if we double the number of moles, then we also double the volume. So important just to know that. So if we double number of moles, we double the volume, or if we half the number of the volume, we half the number of moles. So these two, whatever happens to one happens to the other. And this is very common for all the formulas or all the trends except one of them, which we'll talk about. So Avogadro's is with number and moles. So I mean numbers of moles and volumes. But don't be too caught up with the name of the scientist. All you just gotta know is that how the trend works. So if we increase the number of moles, does volume increase or decrease? You just have to know that. You don't have to know who made it up. And so Boyle's law has to do with pressure and volume. And so this is the only one where it's inverse. So pressure goes up, volume goes down. This is the only one like this. And it follows like a similar rule like how the other one did. If one is doubled, the other one is doubled, but it's the opposite. So if one is doubled, the opposite of doubling something is dividing by 2 or halving it. So in this case, we have 10 liters and 1 atm, so 10 liter volume and 1 atm pressure. So we doubled pressure from 1 atm to 2 atm here, And notice how the volume was halved. So remember, if one is doubled, the other one does the opposite when it's inverse. So the other one was halved. And another cool thing is you can check if you're correct is 10 times 1 is 10, 2 times 5 is also 10. So they always multiply to the same number like this. It should always be like this. And here's another chart showing pretty much the same thing. We have a volume of 10 liters at 1 ATM. Notice the x-axis is pressure, y-axis is volume. And then we go to 2 ATMs, and notice how when we doubled the pressure, the volume decreased by 1/2. And then also, again, if we double the pressure, so we went from 2 to 4 to pressure, the volume also decreased by half. So it'll always follow that same ratio. So whatever happens to one, the opposite happens to the other unit. And that's only for this one because it's an inverse. Then we have Charles' law, which has to do with volume and temperature. And so if we increase the temperature, we increase the volume. And oh yeah, by the way, you can always think about it in the terms of collision. So in this case, if we increase the temperature, the particles start moving even faster, so they collide more often with the walls. And if they collide more often, the volume will increase because there's more force on the container. So notice how, again, we went from 150 to 300, so we doubled the temperature. So what do you expect to happen with the volume? And you're right if you said it's gonna double, and it is. In fact, it went from 300 milliliters to 600, so that's definitely doubling. And then we have the a graph showing this trend, and so the same thing happened. So we went from 150 Kelvin to 300, and notice how the volume doubled. And notice how it follows like a nice straight line, so we can predict pretty much any point on this line at different temperatures. So this is in fact how they predicted or estimated absolute zero. So they got a line like this and made a chart, and they just went all the way back until this line gets to zero. And so zero is when the particles stop moving, so absolute zero. And this in fact is pretty accurate. So this is a cool way that how Charles' law was used to find absolute zero. And then the last law is Lusak's law, which has to do with pressure and temperature. And so if we increase temperature, the pressure will increase, and the only difference between Charles and Lusak's law is Lusak's law has to do with like a rigid container, so a container that can't change shape. So Charles' law would apply to like a balloon because a balloon can definitely stretch because it's elastic. But Lusak's law has to do with like rigid containers like a can or like a tank like this. So if the volume cannot increase, then the pressure will definitely increase. So if we double the temperature, what's going to happen to the pressure? And it's going to double because it's a direct relationship, so whatever happens to one happens to the other. So we went from 300 to 600, 100 to 200, so they definitely both doubled. And then same thing happens, and so if we multiply 200 times 2.5, the temperature must have been multiplied by 2.5 because 2.5 times 200 is 500, so 600 must have been multiplied by 2.5. So that's a cool way to figure it out. So if you know 1 and know how it's multiplied, you just multiply that same number to the temperature and you'll figure out the temperature even though it's not given. And now we get to talk about our fun formula here, which is the combined gas loss formula. So it's P1V1 divided by T1 equals P2V2 divided by T2. And this calculates effects of changes in pressure, volume, and temperature. And for this formula, we have to assume that the number of moles does not change. So important, if number of moles changes, we have to use a different formula, which we'll talk about in the next video. And always remember, we usually temperature must be in Kelvin to do this. Use this formula, and pressure and volume can be in different units, but volume is usually in liters or milliliters, and then pressure must be in the same unit. So pressure and volume can be anything they want as long as it's consistent, but temperature must be in Kelvin. So I always, uh, so beware. And so here's some calculations we're going to do. A pressure on a 411 milliliter sample of gas is decreased from 812 torrs to 790 torrs. What will be the new volume of the gas? So here we write down our formula, first step. Then we pull out what we have. So we have 411 milliliters of the sample of gas. So that's the starting. So that's initial volume, which is V1. Then it's decreased from this pressure, so this is P1, to the second one, so this is P2. And it's asking for the volume of the new gas, so how it changes. So that would be V2 we would need to find. And the cool thing about this is that even though we only have 4 variables here, and we did not talk about temperature, we can ignore temperature for now because we're assuming that the temperature stayed the same. So when some variable is not mentioned, like there can only be like, sometimes they only talk about pressure and volume, sometimes maybe pressure and temperature. But whatever is not mentioned, you can just eliminate from the formula temporarily for this problem. So all we have to do is P1 times V1 equals P2 times V2. And so we plug in the corresponding numbers to the right variable, and we isolate the unknown. So we divide the left side here by 790 in our calculator. So we multiply the top and then divide by the bottom. And after we do that, we should get the new volume, which should be about 422 milliliters of gas. And so here is another problem. So a 10-liter sample of gas is collected at 25 degrees Celsius, then cooled to a new volume of 8.83 liters, while the pressure remained at 1.2 atm. What is the final temperature? And so first we have to write down the formula. So there's our beautiful formula, and then we have the numbers. So we have to pull out and organize our data. So we have 10-liter sample of gas, so that's initial volume, so V1, is collected at 25 degrees Celsius, so that's T1, but remember, convert it to Kelvin, otherwise you'll get it wrong. And then it's cooled to a new volume at 8.83 liters, so that's V2, and the pressure remained constant. So if something remains constant or is not mentioned, we can ignore it. So ignore pressure for now, and we want to solve for T2, by the way. And again, pressure remained constant, so we can eliminate pressure from this whole equation, and T2 is going to be our X. So we plug in the corresponding numbers to all the variables, and so we want to isolate T. So remember in math class, when we have two ratios set equal to each other, we can cross multiply. So we do T2 times 10 equals 8.83 times 298, and this is just in Kelvin. Remember, we convert 25 to degrees Celsius to Kelvin. That's how we got this big number here. And so we divide this right side by 10, and after doing that, we should get an answer of 263 degrees Kelvin. And here is our last problem. A 5-liter balloon is filled with gas at 0.855 atm and 25 degrees Celsius. What is the balloon's volume at STP? And so first we gotta write down our formula. And then we pull out what we have. So we have 5 liters, so that's volume of initial. And then we have 0.855 atm, so that's pressure, initial pressure. And also we have initial temperature. Remember, convert to Kelvin. And then it says, what is the volume at STP? And so we want to find V2, but why? What is STP? Like, where is, how do we know the temperature and pressure, the final temperature and pressure? And STP, by the way, stands for standard temperature and pressure. So that indirectly gives you the pressure and temperature. And you have to memorize this, by the way. So just remember, it's just 0 degrees Celsius or 273 degrees Kelvin and 1 atm. So it's at 1 atmosphere and 0 degrees Celsius or 273 degrees Kelvin, which you have to use. So that indirectly gives us our final temperature and final pressure right here. So we plug in everything, and remember, convert to Kelvin. So this is good. And we want to isolate V, so we essentially just multiply the other side by 273, because V times 1 is essentially just V2. So we just do this whole big old fraction, so 0.855 times 5 times 273. We do that first, then divide by 298, and after doing that we should get the volume, and it should be 3.92 liters. And so pretty much when you're doing those problems, you just write down the formula and pull out what you need, and organize it well. And then remember, convert temperature to Kelvin, and then solve for the unknown after you plug everything in. And so now here, moving on to a quick quiz to see what you learned. A balloon becomes slightly smaller when moved from a mountaintop to the seashore. Which gas law explains this behavior? Is it Lusak's law, Boyle's law, or Charles' law? And don't worry about remembering the laws. So I'm going to give you the correlations. So Lusak's law states that if temperature increases, pressure increases. And remember, this is a rigid container, so these containers can't not change volume. Then we have Boyle's law, which is if pressure increases, volume decreases. So external pressure, so we have more pressure pushing down, that means volume should decrease. And then Charles' law has to do with temperature increasing and volume increasing. So this is for like elastic or flexible containers. So like in this case, a balloon is definitely flexible. So if temperature increases, volume definitely increases. And so let's just go back to the problem. And so we move from a mountaintop to a seashore, and the volume decreased. So to explain it in scientific terms, we know that mountains are higher up in the atmosphere. And remember, in the last video, we talked about air pressure. And at higher temperature, higher elevation, they have less air above us on Earth, because Earth has an atmosphere, and then the air is actually pushing down and has some pressure. And even though you can't feel it because you're used to it, there is some pressure pushing down. And if we're at a mountaintop, because simply there's less atmosphere above us, there's less pressure. But when we go back down to sea level, there is more air pressure because we're lower down, and simply there's more air above us now. So if the pressure increased and only one of them has pressure increasing and volume decreasing, so the correct answer is B. And just remember, if there's more pressure pushing down on that balloon, it's going to be smaller, because just if you're like squishing like a squishy ball, the more force you apply to it, the less volume it's gonna take up. So it's pretty much like squishing something. So that pressure is squishing the balloon, and as we have more and more pressure, the volume gets smaller because there's more force pushing down. So that's why this balloon is getting smaller at the seashore compared to the mountaintop. So, if the temperature of a gas in a flexible container is doubled, the volume will be A halved, B doubled, or C the same. And so here's the trend. So both of them increase. So if temperature increases, volume increases. And remember, they increase by the same factor. So if we double the temperature, the volume will definitely double. So the correct answer is B. And if you're like a visual learner like I am, you can think about it in terms of collision. So if we have higher temperature, the speed of those particles in the balloon are moving so much faster, so they're colliding more often. And because they collide with the walls more often, they increase the volume because there's more energy applied to the wall. So that's why temperature increases volume. And here's the last question. If the pressure of on a gas in a flexible container is halved, the volume will be halved, doubled, or the same. And here is the trend, or the two trends. And so I have this little animation to help you out and visualize this. So here, before we talk about this balloon thing, if the pressure is increased, the external pressure is increased, the volume should decrease, or if the pressure is decreased, volume should increase. And so here's a little thing. So we have a balloon, and normally there's the atmosphere is pushing down, so represented by these two arrows pushing down the balloon, and inside the balloon there's a force pushing out of the balloon. But uh, when we half the pressure, now think about it, there's only one arrow pushing down, but there's still the same amount of force pushing up. And because there's more force inside the balloon can push harder out and it becomes larger. So which of these shows that it became larger? And the correct answer is B. And you didn't have to use that animation. I was just helping, if you're a visual learner like me. And so you can also think about it in terms of a trend. So so the pressure was halved, so pressure definitely went down. That means volume must have went up. And remember, this is the only weird one where it's an inverse relationship. So if pressure went down by 1/2, that means the volume increased by 2. So they're opposite. So if pressure went down by 1/3, volume would increase by 3. So they're always like a reciprocal. And that is it for today. So today we talked about the 4 trends with gases and some scientists. And so don't be too caught up with the names of the scientists. It's good to know who they are, but don't worry, you won't be tested. You'll be tested on what the relationships are, not the scientists' names and what they made up. And also we talked about the combined gas laws formula, which is P1V1 divided by temperature, equals P2V2 divided by temperature of the final. And so remember, just plug in everything and then solve. And most importantly, make sure you convert that temperature to Kelvin. And so just keep on practicing that math formula and some problems. I'm sure you get the hang of it. And just think about the pressure, temperature, and volume. Think of collisions. And always remember, ask your teacher if you have any questions. And I hope this helped you, and we'll see you next time when we talk about ideal gas laws.